Welcome back to Halogenoalkanes. In our last video we had a look at our big long and practical method of preparing halogenoalkanes, in particular 1-bromobutane from butanol, so the preparation of halogenoalkanes from their corresponding alcohol and reacting that with a hydrogen halide. In that example it was hydrogen bromide. What we're going to do in this video is look through your notes on page 15 and 16 to have a look at some other methods of preparing halogenoalkanes. And the good news with these methods is we're not going to look at a step-by-step method as such, and just introduce you to the reaction and ways in which we can see those halogenoalkanes being prepared from different reactants. So the second method of preparing halogenoalkanes is by substitution using alcohols and phosphorus pentabromide, or if we wanted to make the chloride, we could do phosphorus pentachloride. This method's not as common because it doesn't give us a very good yield. But we could make 1-bromobutane this way, and we start again with the alcohol, but rather than reacting it with hydrogen bromide like we did in our big practical method, we're reacting it with phosphorus pentabromide. So the left-hand side of the equation is going to be our butanol, C4H9OH, plus phosphorus pentabromide, PBr5. That's going to give us 1-bromobutane, C4H9Br. It gives us another substance called phosphorus oxybromide, which has the formula POBr3. And then think about what we're left with. The oxygen from the alcohol is now within our phosphorus oxybromide. If you think about the bromine atoms, we've got 5 here, and we've got 1 there, plus 3 here, which is 4, so we still have 1 bromine left, and we also have this hydrogen from the alcohol. So that's our final product is HBr. In terms of your observations for this reaction, the phosphorus pentabromide is a yellow solid, so when this reacts with our liquid alcohol, that yellow solid will disappear, so solid disappearing will be one of your observations. Then if we think about our products, well, hydrogen bromide, remember that comes off as misty fumes. If you remember back to your halogens topic, we would have talked about misty fumes of HBr or HCl or HI, so that is misty fumes. So in terms of coding observations, you could say yellow solid disappears, misty fumes, and other observations you could quote would be heat released and vigorous reaction. So this reaction releases a lot of heat, and it's a vigorous reaction. Phosphorus pentabromide is quite harmful, so we have to use it in the fume cupboard. But this is a vigorous reaction, so we only use small amounts of it, and it does lead to a poor yield, so we don't often make halogenoalkanes this way. The next method we can use is by reacting alcohols again, but this time with phosphorus tribromide. So the previous example was the reaction of alcohols with phosphorus pentabromide. This time we can use phosphorus tribromide or phosphorus trichloride or so on. So again, we take the corresponding alcohol, reflux it with phosphorus tribromide, and that will produce our corresponding halogenoalkane. But again, this results in poor yield, so it's not generally used, but it is a method that will make the halogenoalkane. So if we write our equation for this reaction again, for making 1-bromobutane from butanol, which is C4H9OH, that reacts with phosphorus tribromide, PBr3. That's going to give us our corresponding halogenoalkane, which is C4H9Br. And our other product is phosphorus acid, which has the formula H3PO3. Phosphoric acid has an extra oxygen, it would be H3PO4, but this is phosphorus acid. In terms of observations for this reaction, there's not an awful lot to be noted in this reaction, because there's no gases being produced, no solid being added that disappears or anything. Butanol is going to be a colourless liquid, as is our product, and our side product of phosphoric acid will be a colourless solution. Phosphorus tribromide, this time is a colourless liquid which has a pungent odour, so that would be observed of the phosphorus tribromide itself, but there's no specific observations that you need to know for the this reaction. So again, this method's not really used very much because it has poor yields. Your next method is also preparing from the corresponding alcohol, but this time using thionyl chloride, which has the formula SOCl2. Thionyl chloride would have this structure in terms of bonding, although that doesn't reflect the true shape of the molecule, but that gives you an idea of the bonding. And it will react with an alcohol to produce the corresponding halogenoalkane. So it says here, for example, to make chloroethane. So if we want to make chloroethane, then the corresponding alcohol is ethanol. That has the formula C2H5OH. So again, eth means 2 carbons, and then one of the hydrogens, if we were thinking of ethane, one of the hydrogens is replaced by the OH group to make it an alcohol. So that is the formula for ethanol. Reacts with thionyl chloride, SOCl2, to produce the corresponding halogenoalkane, which is C2H5Cl. That's chloroethane. We don't need a locant number there because there's only one halogen. And it is always going to be connected to the first carbon. Side products here are sulfur dioxide, SO2, 1 oxygen from the thionyl chloride and 1 oxygen from the alcohol. And your other product would be HCl. Again, you don't specifically need to know observations for this reaction, but you can apply it from other topics. So, for example, we know that sulfur dioxide has a pungent odour, and we know that from our halogens topic. It has a pungent odour, and HCl would produce misty fumes, so those would be observations you could learn for that reaction. So the reactions on this page and the previous method of preparation of 1-bromobutane from butanol, those are all new methods of preparation. Those are all reactions that you haven't met before. But we're going to look just at 2 more ways of making halogenoalkanes, which we've actually seen before in our alkanes and alkenes topics. So this is where we start to see the link between our different organic chemistry topics. We start to see that the reaction we meet in one topic will actually be the preparation of the type of compound in a different topic. So method number 5 is preparing halogenoalkanes from alkanes and a halogen. So we met this in our alkanes topic, so this is not new. So in this reaction, an alkane and a halogen react together in the presence of UV light, because remember, alkanes are very unreactive, and so we need UV light to get it started. That gives a halogenoalkane and a hydrogen halide. So we'll look at the example which we looked at back in our alkanes topic of methane reacting with chlorine to produce chloromethane and hydrogen chloride. You could try yourself to see if you can remember the mechanism for this reaction, but I'm going to take you through it now. So if you feel confident, maybe pause the video. You could look back at your notes from the alkanes topic and try and write it in yourself, or you can watch as I take you through it now. So you don't have an awful lot of room here, so you will need to make this quite smaller. You could do it on a different page if you wish. But what we have, first of all, is our initiation step, which will involve a molecule being split up into 2 radicals. A molecule going to a radical and another radical. So what we start with is our molecule of chlorine. So I'm going to do this in a couple of different colours. So chlorine, a blue one, and I'll do a green one as well, just to show where the electrons go. You don't have to do this in your exam, you don't have to colour code it, but just to show where the electrons go. So if you remember back from our alkanes topic, this mechanism involves the homolytic fission of this bond. What that means is the bond breaks in such a way that each of the atoms gets 1 electron, so it breaks symmetrically as such, it breaks so that the particles produced are identical. So this electron would go to this chlorine atom, and we use a single-headed arrow in this case, unlike our mechanism with alkenes, which have double-headed arrows. We have single-headed arrows here because it's the movement of 1 electron. That blue electron will then move over here, And what we'll produce as a result are 2 chlorine radicals. Remember, a radical is just a particle with an unpaired electron, and therefore it is very, very reactive because it wants to react and essentially get another electron to complete that pair. So that's the initiation step. We need that step in order for the reaction to get started. Then we've got what we call our propagation step. And our propagation step will involve a molecule reacting with a radical to give a radical and a molecule. In other words, the thing that starts off as a molecule will then become a radical, and the radical will then become a molecule again. So what happens now is initially our methane will react with a chlorine radical. So if you draw methane first of all, along with a chlorine radical. And what will happen here is the carbon-hydrogen bond, which I've indicated here with my electron pair, will break homolytically, and the hydrogen will form a bond with the chlorine, and then we'll get a methyl radical, so a CH3 with an unpaired electron. Let's show that in terms of our electron movement. So we see this dot of an electron, doesn't matter which way you do it, but we usually represent our radical with a dot. So I'll show that electron going into the carbon. And then this X, the other electron, will be used to form a bond with the chlorine. And the other bond to make up that electron pair of the covalent bond between hydrogen and chlorine will be the dot, the unpaired electron from the chlorine radical. So that will produce a methyl radical, which we can represent as CH3 dot, and will also form hydrogen chloride. So HCl, and that has formed from the X of the initial carbon-hydrogen bond and the dot of the chlorine radical. But it doesn't stop there, because that's not what we want. We want our product of chloromethane. So there's a second stage of the propagation step, and that's where the methyl radical, the CH3 dot, reacts with another molecule of chlorine. And ultimately here we want to form chloromethane. How we do that is we form a bond between our unpaired electron of our methyl radical and one of the electrons from the chlorine-chlorine bond. That will cause the chlorine-chlorine bond to break homolytically, so that electron goes to the other chlorine atom. And so what you'll see is that we'll form another chlorine radical, so this reaction can continue. So what we'll produce here is our chloromethane. And that's with the blue chlorine atom. Won't be blue in real life, but just for our representation of the movement of electrons. So that's our chloromethane, and will also produce another chlorine radical, which can then go on and keep the reaction going. That can react with another methane molecule. So that's our propagation step. Then finally, we've got our termination step, which involves 2 radicals joining together to form a molecule. So we can get here because our radicals have an unpaired electron. If we have 2 of those come together, they can form a covalent bond, and therefore they'll become a normal molecule as such. So there's 3 different ways that we can do this, because we have 2 different radical particles in this reaction. So we could have a chlorine reacting with another chlorine radical to produce Cl2. We could have 2 methyl radicals reacting together, and that would give us ethane, C2H6. Or we could have a methyl reacting with a chlorine radical, and that would also give us our desired product as well, chloromethane. So CH3 plus a chlorine radical, that could give us CH3Cl, which is our desired product. So as you can see, ultimately our product is CH3Cl, and that is a halogenoalkane. So this reaction that we met in our alkanes topic, the photochemical substitution of alkanes with a halogen, that is one way of preparing a halogenoalkane. So that's one other method of preparing a halogenoalkane. And the final method, you'll be glad to hear, number 6, is another reaction that we have seen, the reaction of alkenes with a hydrogen halide. So again, this is something that we saw in our alkenes topic. Again, involves a mechanism, but this time quite a different mechanism. This time it is electrophilic addition. So you can see here the reaction is the example that we've been given is ethene reacting with hydrogen chloride. So we had a lot of practice of this in our alkenes topic. Again, give yourself a challenge and try and draw this mechanism even in pencil, and if you're wrong you can edit it or try it on a rough piece of paper and then check it with this video. This is a reaction that mechanism that we drew out quite a few times within our alkenes topic, so see if you can give it a go. So we start off with our two reactants, ethene and hydrogen chloride. And our hydrogen chloride is our electrophile. Remember, that just means loves electrons, because the H end, the hydrogen end, will be delta positive, and the chlorine end will be delta negative because it's more electronegative. So this contains a polar bond. So that slightly positive end of the hydrogen chloride will approach the carbon-carbon double bond because it is a region of high electron density. Remember that your carbon-carbon double bond is made up of two pairs of electrons. One will be a sigma bond, and one will be a pi bond, so those electrons will be in the pi orbital of that carbon-carbon double bond. So essentially, what we show is a curly arrow and a double-headed arrow this time because we're representing the movement of an electron pair rather than just one electron. So the electrons jump out from the carbon-carbon double bond, in particular the pi bond of that carbon-carbon double bond, and that electron pair is used to form a bond with the hydrogen. Hydrogen can only have one bond, so its bond between hydrogen and chlorine breaks, and that electron pair that is keeping the hydrogen and chlorine together will then move to your chlorine, and that will become a chloride ion. So even if you're going through this with me, maybe pause at this point, see if you can work out, well, what molecule are we going to form with your charges and everything, and then we'll go from there. So what we form here is the hydrogen will bond to one of our carbon atoms. It's a symmetrical alkene, so it doesn't matter which one you draw it on. I'm just going to draw it on the one on the left. As a result, the carbon on the right has lost its share of a pair of electrons. In other words, it's lost one electron, and so it has a positive charge. Then what else we'll have here to essentially balance out the charge is a chloride ion. Because at this stage, when that hydrogen-chlorine bond broke, the pair of electrons went to chlorine, so it now has a lone pair of electrons and is a chloride ion. So what happens now? Well, simply the chloride ion uses its pair of electrons to form a bond with the carbon atom here. This is a carbocation. It's carbon with a positive charge on it. So that chloride ion is attracted to the positive charge and uses that pair of electrons to form a covalent bond with that carbocation. So let's draw our final product then. And what we can see is the hydrogen chloride molecule has added what we call a cross the double bond. Essentially, the bond between hydrogen and chlorine has broken. The hydrogen has bonded to one carbon and the chlorine is bonded to the other carbon. And as a result, there's only now a single bond between the two carbon atoms. So that is the electrophilic addition of hydrogen chloride to ethene. And we can use this as a general method of preparing halogenoalkanes. We can see that our product here is simply chloroethane. So that is a halogenoalkane. It's an alkane that has had one of the hydrogen atoms substituted with a halogen atom. So this is a halogenoalkane, and we've made this by the reaction that we saw in our alkenes topic, taking an alkane and reacting it with a hydrogen halide, in this example hydrogen chloride. So these last two methods are actually reactions that you've seen before. So if you learnt those well in our alkenes and alkenes topic, then there's nothing new to learn here. So let me just run you quickly through the methods of preparing halogenoalkanes that we've met. So the first method we met over on page 10, or starting on page 10 anyway, was the reaction of a primary alcohol with a hydrogen halide, and that will give us a primary halogenoalkane. So that was the big long reaction that we looked at, and we looked at the method of preparation in quite a lot of detail, and that's the most common way to make a halogenoalkane in the lab, by reacting a primary alcohol with hydrogen halide, and that will be formed in situ. The hydrogen halide will be formed in situ from most likely the sodium salt of the halide and concentrated sulfuric acid. Next method we looked at on page 15 was the reaction of an alcohol with PCl5 or PBr5, phosphorus pentachloride or phosphorus pentabromide. So that will produce the corresponding halogenoalkane from the alcohol. We can also react an alcohol with PCl3 or PBr3. You just get essentially different side products, but the reaction is essentially the same. And all of these methods involve reflux as a method of preparation. Fourth method we looked at was reacting an alcohol with thionyl chloride, SOCl2. So this method produces a higher yield than the PCl5 and the PCl3. So it's a slightly bit different or better method of preparation. So you can see the first four involve an alcohol plus another reactant to produce your corresponding halogenoalkane. And we'll see these some of these reactions again in our alcohols topic, so they should be familiar by that stage. Then our fifth method of preparation was the reaction of an alkane with a halogen, and that's our photochemical substitution that we met in our alkanes topic. So that's one that we've met before, an alkane reacting with a halogen. And then lastly, one that we met in our alkenes topic is the electrophilic addition of an alkene with a hydrogen halide, and that again will produce our halogenoalkane. So there are 6 methods all in all of preparing a halogenoalkane, and the ones that you should know in most detail are those last two, because you need to know the mechanism as well, and ones that we've met in another topic.